Okay, so here we talk about the Stokes theorem. Stokes theorem. So similar to divergence theorem, it is also another generalization of the fundamental theorem of calculus. But here we have a double integral. We have double integral here. We have triple integral here, and then this divergence is something like a derivative. And here we have a line integral, which is somehow like a single integral, and then here we have a double integral. And then here we have a curl of the vector field. So for the curl of the vector field, this is also like the first derivative. But yeah, but of course we have the cross product here. So after the curl of the vector field, this is still another vector field, and then we need to have the dot product with this area vector. Dot product with this area vector. Okay, so so here we can see this is a closed boundary, or you can regard it as a Ampersand loop denoted by this round sigma. So this this line integral is evaluate over this closed loop, or the round sigma. Yeah, of course there are f vector over the whole space, and then on the right side we try to evaluate the curl of f, and then we try to calculate the double integral of the curl of f for this area. This area is bounded by this closed loop, so we call this area sigma. So yeah, it's somehow like this. And similarly, if you are interested in the proof, you can try to check this link whether it still works, or maybe you can just check it. You just try to Google it, and you should probably find some proof. Yeah, it takes a few pages to really prove this one, but yeah. So yeah, so if you are really interested, you can try to check it out. But otherwise, here I just try to simply explain the interpretation of this Stokes theorem. So as I mentioned last time, the curl is like how the vector field is rotating. So you can simply imagine when you consider the curl of f on the right side, it is like for example, for this point, you try to calculate how this vector field is rotating, and then for the adjacent point, it is also rotating. Okay, so you can imagine that. Suppose maybe I did not draw very well. Maybe maybe for this one. Maybe for this one. For this one, it is rotating like this. So you can imagine this point. At this point, this is pointing to the left side. This is pointing to the right side. So for adjacent point within this area, these two vectors are canceling each other. So the only remaining one is simply lies on the boundary. So that's the interpretation of this equation, or this Stokes theorem. So on the right side, we try to evaluate the curl of f over this whole area, and then all the adjacent points, some of the curl will cancel each other. Only the boundary remains. So finally, it becomes the line integral of f over this boundary. So all the inside components are canceling each other. So here it says the line integral of the vector field over the boundary of the surface equals the surface integral of the curl of the vector field over that surface. So this is the Stokes theorem. So these two theorem looks quite complicated, but yeah. And actually we only need to use the result, so we don't try to go too deep into it. Okay, so here we try to evaluate. We try to actually derive why the differential form of the Gauss law will be like this. So here is the Gauss law you are familiar with, which is the integral form. And as I mentioned last time, we don't rewrite Q enclosed. Rather than that, we try to write it into a triple integral. So this triple integral is like the rho. Rho is the charge density, and then we try to integrate it over the volume. Then this is the total charge. Total charge. Of course, this volume is enclosed by the Gaussian surface. So this Q enclosed is written like this. And then we try to apply the divergence theorem. So for the divergence theorem, we have the surface integral on the left side, and then on the right side we have a triple integral, but we have another derivative like operator, which is called the divergence. We take the divergence of E and then we integrate it for the whole volume. So this is the divergence theorem applied for the E field. So this stuff is actually the same as this one, which means that we have this triple integral equals to this term. So we put this one here and then put this one here. Okay, so yeah, actually for these two triple integral, they are integrating over the same volume. And actually, this volume can be arbitrarily chosen, which means that if this integral is equal to this triple integral for the same volume, and then this volume can be arbitrarily chosen, which means that over the whole space, all the point, all the integrand should equal to each other, which means that the divergence of E should be equal to rho over epsilon naught. And also we just try to put this one inside because this is just a constant. So just put it inside, and then these two triple integrals are equal to each other, and then for arbitrary volume, so which means that the integrand should be equal to each other. So finally we have this divergence of E equals rho over epsilon naught. Okay, and similarly for the magnetic version of the Gauss law, of course it is like something like this, B dot dA equals 0. So going through the same thing, but yeah, on the right side of course it is 0. So finally we can come up with a divergence of B equals 0. So they just look alike. So only the difference is this is E, this is B, this is the charge density over the epsilon naught, this is the 0 because we have no magnetic monopole. Okay, so we already derived the two Gauss law in differential form. And then for the Faradays law, of course, we do not use divergence theorem anymore. We would like to use the Stokes theorem. Okay, so actually this is the Faradays law you study in chapter 30. So on the left side, this is the EMF. This is the EMF. On the right side, originally it is written as a negative d phi b dt. Originally we would write it like this. And here we also try to express this phi of b, which is the magnetic flux, into this double integral. So yeah, and then of course it's not a closed integral, so we don't have a circle here. And then we try to apply the Stokes theorem on the left side. So for the Stokes theorem, we have the line integral of a vector field, and on the right hand side we have a double integral over the area enclosed by the Ampersand loop. And then for the integrand of the on the right side, it is the curl of E. So this is the Stokes theorem applied for the E field. And yeah, so this one is actually the same as this one, which means that the right side, this double integral equals to this term. So we put this one here, and then we need to put this one here. Okay, so similarly, for this double integral, before we go to this here, we try to put this one inside the integral sign. Yeah, of course, for mathematical department, they may be considered whether putting this derivative inside the integral, whether it will be converged or whether it will change the result. But yeah, generally for us, for engineering students, we just assume it this one is converged, and then it doesn't make any problem. But and usually if the B field or the other maybe the change is continuous, then usually it doesn't make much difference unless this integration is diverged. Sometimes it may diverge. So, and it really means yeah, there are some cases that you can try to make some integration that you put this one inside, and then it may make a different result. But yeah, it is quite rare. But so here we try to believe that putting this derivative inside the double integral doesn't make any problem. And the only thing is that before we put this one inside the integration, we use the ordinary differentiation. But if we need to put this one inside the integral, we need to use the partial derivative, because after calculating this one, this double integral, it becomes a scalar. So it probably only related to the t. But if we need to put this one inside, the B field is a function of x, y, z, and t, something like that. So we need to use partial derivative rather than ordinary derivative. Okay, so after making this step, then we can make a similar argument that this integration and this integration, this double integral and this double integral are actually the same, or maybe also you can put this one inside. And so for this area, it can be arbitrarily chosen, which means that for this double integral is equal to this double integral. For arbitrary area, then the integrand, or this integrand, is equal to this integrand with this negative sign. So finally, we have the curl of E equals negative partial B partial T. So this is the differential form of the Faradays law. Okay, so the derivation here is not difficult, I think. Okay, so this is the last one, which is the Ampersand law. So this is the Ampersand law. So this is a line integral of a b dot ds, and the right side we have mu 0. Originally, this is the I enclosed. We try to make this one. Yeah, this is I enclosed, the current enclosed by this Ampersand loop. And here we also try to express this I enclosed as a double integral, which means that it is something like this is the boundary, and then we try to evaluate the current J. This is the current density, yeah, and we try to integrate the current density over the whole area. And then here, this is the displacement current. This is originally epsilon naught d phi e dt, which is the displacement current. And similarly, we try to express this phi e into a double integral. So we have epsilon naught d dt, and then the double integral of the E field. Okay, so here we also apply the Stokes theorem on the left side. Apply the Stokes theorem on the left side. So this is the line integral of a B field, and then on the right side it is a double integral, and then we have the curl of the B. Okay, so this one is the same as this one, which means that this double integral, we put it here, which is equal to this whole term. And then we try to distribute it here, distribute. And also we try to put this one inside. So this d dt for the E field becomes partial E partial t. So we just put it inside. Also we put this epsilon naught inside. Okay, so, and actually this area is actually the same for this area, so that these two integrals can be added together. So finally, this becomes mu naught, we put it here, and then we have a j plus epsilon naught times partial E partial t, put it here. So this is the whole integral on the right side. Okay, and similarly, these two double integration are equal to each other for arbitrary area. So the integrand should equal to each other, which means that the curl of B equals mu naught times J, the current density, plus epsilon naught times partial E partial t. So this is the differential form of the Ampere's law. So in summary, the Maxwell equation, we try to use the Gauss law to derive the the Gauss theorem or the divergence theorem to derive the differential form for the Gauss laws, the two Gauss laws, like this. And then we use the Stokes theorem to derive the differential form for the Faradays law and also the Ampere's law, like this and this. So all these four are the differential form for the Maxwell equation. And as I mentioned, in the textbook, we just use this one, but but for mathematical calculation, usually for computer-aided program, the differential form should be useful than the integration, because calculating integration probably need the Riemann sum, so you need to do many of the add and multiply. And for this differential form is like solving a differential equation, and then you can use some numerical method like Newton's method or whatever method, finite element method, to really solve the E field, B field for different rho or different j. Because you can see actually for this Maxwell equation, the unknown are E field and B field in different time, and then x, y, z. So there are 4 independent variables, like the independent variable as the independent variables are the t, x, y, z. T, x, y, z, which means that we have a e of x, y, z, t, t, and then we have a b of x, y, z, t, something like this. So yeah, so E and B are function of x, y, z, t. And then also E has a different component. Maybe E can point to x direction, y direction, z direction. And then also B field can also point to x direction, y direction, z direction. Okay, so there are totally six unknown. If you consider it in Cartesian coordinate, it is like we have Ex, Ey, Ez, and then we have Bx, By, Bz, something like that. And then this row and J are so-called the sources, two sources. Which means that in the space, if we put some charge there or put some current there, it can generate the E field and B field. And if the source is also time varying, which means that sometimes the charge is here, sometimes the charge is there, or if the current is flowing, or maybe it can also be changing, maybe increasing or decreasing from time to time. It can generate some E field, B field, and of course in chapter 33, which means the next chapter we'll talk about how the EM wave or the electromagnetic wave is generated. What is the mechanism? Actually, the EM wave is the solution for the Maxwell equation. And of course, we can try to derive the wave equation from the Maxwell equation. And actually, we'll talk about it in the next chapter. Okay, so before we end this note, we have something more to talk about, which is the conservation of charge. So the conservation of charge, in chapter 21, we just talk about the conservation of charges means that we cannot create or we cannot diminish the charge. But here when we talk about the conservation of charge, it is related to an equation. And actually, this equation is compatible to the Maxwell equation in this form. Okay, so here we can see the meaning here. And of course, before we derive that, we can try to write the integration form of the conservation of charge. Here we still define rho is the charge density over the space, and then J is the current density. Okay, so these two are so-called the sources for the Maxwell equation. Okay, so and actually there are some relationship between them. Okay, so here the first one is that I equals the double integral of the surface integral of a J dot dA. So in chapter 26, when we talk about this definition, it is written like I equals double integration of a J dot dA. So without this negative sign and without this circle. Okay, so it only defined for a cross-section area. So a cross-section area, or if we have a J here, then we can really calculate the I over the whole space. But here, we try to consider a volume. And then of course we try to define a closed surface, something like the Gaussian surface. Actually, we should call it the closed surface rather than Gaussian surface. And then we try to calculate the current. And then the current, as much as this is a closed surface, we can really divide the direction with the negative sign, which means that if the current is throwing out, then it is it is negative. So we consider the current going in this region. And for this surface integral, we always define that dA is pointing outside. dA is always pointing outside, which means that if the J is flowing out, this is a positive value. This is a positive value. But here we try to define the I to be pointing inside. Okay, so here this is a surface integral, and of course we can try to apply the divergence theorem here. So this is a double integral of J. So here we have a divergence of J, and then this negative sign is putting inside. And then this is double integral. We have a triple integral here, so that this is the divergence theorem. And then also we have I equals dq dt. Q is the charge inside this volume. That's why we need to assume that I is positive when the I is flowing into this region, because if I is flowing into this region, which means that the charge will increase. So I equals dq dt. Of course, you can make it like I equals negative dq dt, but here we have a positive sign, so that everything matches each other. Okay, so here we also try to express this Q inside this volume as the density, the triple integral of the charge density over this volume. So we have a d dt here, and then Q is the triple integral of the charge density. And similar, when we try to put this derivative inside the integral, we make it like a partial derivative. So we have partial rho partial t here, dv. Okay, so here this is I, which means that this triple integral equals this triple integral, which means that we have this one equal this one, and then for arbitrary volume, which means that the integrand should equal to each other. So finally we have, okay, so this is a typo mistake. It should be like this. Okay, so finally we have a partial rho partial t equals, we have a partial rho partial t equals negative divergence of J. And then we try to move this one to the left side. We have a partial rho partial t plus divergence of J equals 0. And this is actually the conservation of charge. Okay, so here we try to explain this charge conservation is compatible to the Maxwell equation in this form. Because when we talk about the Ampersand Law in chapter 29, we only have this one, B dot ds equals mu naught I enclosed. And when we consider the corresponding differential form, which is like curl of B equals negative, positive mu 0 j, something like this, without this one. And then in chapter 32, we also introduce, this is a displacement current, which means that we try to add an additional term on the right side. Okay, and then I just tell you that this is more correct. Which means we try to add mu 0 epsilon naught and then d phi e dt. This is the displacement current, and then we add the terms here, and then it becomes epsilon naught partial e partial t, like this. Okay, so at that time we tell you that this is more correct than this one, because it not only covers the static current but also the displacement current. But yeah, maybe you have question that whether we need to add the third term, the fourth term to make it even more correct. And here the answer is no, because up to this version, it is compatible to the conservation of charge. If we further add more, then it will not compatible with the conservation of charge anymore. Okay, so here is the explanation of why the Maxwell equation in this form is compatible to the conservation of charge. Okay, so originally we have this is the Ampersand Law. We try to take the divergence on both sides, on both sides, which means that it becomes this one, and then we try to take the divergence. So take the divergence is like divergence of curl of B, and usually we won't write the parenthesis here. So this is just an explanation that this one evaluate first, and then this evaluate later. But usually we only write it like this, because you cannot, maybe you can evaluate it first. But this becomes another operator. It becomes the Laplacian. But anyway, on the left side is the divergence, and then of the curl of the B. And then on the right side, this is just a scalar. The mu naught is just a scalar, so that we can put this one inside. So we have a mu naught times divergence of J here. And then this one also putting inside. We don't have a 0 here. Okay, on J here. So we put this one, we distribute this one inside, and then epsilon naught is also a constant. So we have a epsilon naught, and then this one directly go inside. So we have a partial t here, partial t here, and then the divergence directly go here. We have a divergence of E. And actually there is a theorem called this is the divergence of a curl is 0. Actually, you can try to verify it in the Cartesian coordinate. Yeah, you can just try. If you don't believe, you can just try to use the original definition here. So this is the definition. This is the curl of F, and then you try to take the divergence. The divergence is it's like taking the x derivative, the x component, and then take the partial derivative with respect to x, and then plus the y and the c. Which means that if we try to take the derivative with respect to x here, it becomes 0. It also becomes 0. Okay, actually you can, if you have interest, you can just try to verify yourself. But so try to believe it here. So the left side will become 0, which means that the right side should also be 0. And here, as much as the right side is 0, and also we have the Gauss Law. The divergence of E is rho over epsilon naught. So we can just put this one, which means that put the rho over epsilon naught into here. And then 1 over epsilon naught and this epsilon naught can cancel each other. So finally, this one becomes partial rho partial t. And then on the right side, we have mu 0, the divergence of J plus partial rho partial t. And this is actually the conservation of charge. So, and for the conservation of charge, this one is 0, which means that 0 equals 0. So it's okay. We cannot solve anything because they are compatible to each other. They are dependent. Equation. Just like when when you learn the try to learn the joint algebraic equation, something like x plus 2y equals 4, and then 2x plus 4y equals 8, then you cannot solve the unique solution, because if you multiply 2 and then just subtract this one, and then it becomes 0 minus 0, and then there will be infinite many solutions for this equation, just like x equals t, y equals a minus 2t. For arbitrary t is a real number, then there will be infinite solution. So, and we will call these two equations are dependent to each other. Okay, so as this case, in this case, this is 0, so we have 0 equals 0, which means that the charge conservation or the conservation of charge are compatible with Maxwell equation. They are dependent on to each other, Okay, and that's why they're compatible to each other. Otherwise, if we add further term, which makes the right side is not 0, it's non-zero, and non-zero equals 0, so it won't be correct. So we can say that this is the most correct case for the Ampere's law. Okay. So here, okay.